All right, good morning, everyone. It's 8:30, so we'll start with this session on self-controlled and other method stuff. But first, congratulations that you made it to this early hour. People are still coming in, so it's going to be an exciting session, I think, with interesting talks. My name is Olaf Klungel, Utrecht University, and I'm co-chairing this meeting with my colleague over here.
And I'm Hiraku Kumamoru from University of Tokyo.
And without further ado, I would like to invite the first speaker, Jesper Halles from the University of Southern Denmark. And he's going to talk about hypersensitivity of self-controlled designs towards exposure misclassification when there is abundant chronic use, a simulation study.
Seems to work. Good morning, everyone. The title you just heard, Hypersensitivity of Self-Controlled Designs Towards Exposure Misclassification When There is Abundant Chronic Use, a simulation study. I am Jesper Halles. I'm from University of Southern Denmark. Last year, when we had the meeting in Copenhagen, we tried to coin the concept of true IGBE heroes, those who show up after the farewell party early in the morning to attend a hardcore methods paper. So you, my friends, are true IGBE heroes. As are my brilliant co-authors, one of which, Lars Christian Lund, you'll hear later on this session. Disclosures, I don't believe the commercial disclosures apply, but some of the intellectual might. Malcolm McClure developed the case crossover design, and I developed the sequence symmetry analysis, and both of these will be tested in this simulation study. The background is of self-controlled designs, as most of you would know. They compare the individual's exposure at an outcome date with the same individual's exposure at other times. And thereby, they all become robust to confounders that are stable over time. They are becoming increasingly popular in pharmacoepidemiology. People who are treated at all times should drop out in all of these designs, and that exactly might create a problem that I'll try to illustrate. Imagine this scenario. These are timelines. Red lines means that you are treated, and green lines means you're untreated. And there are just two individuals who seem to have intermittent exposure. And those are the only two who should contribute to the case crossover estimate. And they should only contribute if they have discordant exposure at the outcome at the reference date. So this is a simple, crude case crossover design I've illustrated here. And it seems clear to me that it doesn't take much, just a tiny bit of exposure misclassification, then some of these chronic users will remain in the study and will appear to have discordant exposure and contribute to the estimate. And since this is likely non-differential misclassification, this will lead to a bias towards the null. And also, since there are now more people contributing to the estimate, both those who have true discordance and those who have false discordance, the confidence intervals will become too narrow. In the home court of a case crossover design, where nearly all have intermittent exposure, this is much less of a problem, I would suspect, because even small misclassification here would not completely distort the pattern and increase the number of people with apparent discordant exposure. How would such exposure misclassification arise? It has to do with how you build treatment episodes in pharmacoepi. Nearly all methods assign a period of usage to each prescription, and if that period of usage overlaps the beginning of the following prescription, they are believed to belong to the same treatment episode. And if it does not overlap with the following prescription, there is a gap. What would happen if you assign a too short period to all of these prescriptions? Then you would have all of these artificial gaps that would be, I suspect, quite toxic for a self-controlled analysis. So my hypothesis was that in self-controlled designs, a small amount of exposure misclassification leads to a strong bias towards the null, particularly when there are many chronic users, and these biased estimates have unduly narrow confidence intervals. While preparing this, I was reminded of the famous Dunning-Kruger effect in psychology. You could say that these designs under these circumstances are incompetent. They produce wrong results, and yet they are overly confident in these wrong results. Simulation study was based on around 40,000 real-life citalopram users from the prescription database of Southern Denmark. I chose citalopram and SSRI because it has a mixture of chronic and short-term users. Episode building, I had a rule which I declared was reflecting true exposure, namely that there would be an intake of 1 tablet per day, and I added a grace period on top of that of 90 days. Misclassification was introduced by shortening these grace periods, thereby producing artificial gaps. I simulated the outcomes only for the true exposure profile, assuming a constant rate within exposed and non-exposed intervals, and applying a rate ratio for truly exposed follow-up. The design specifications, shortly, cohort study, analyzed as treated without censoring. I had a one-to-one mix of users and simulated non-users. Case crossover and case time control, focal washout and reference dates, 4 of them set with 60 days between them. Self-controlled case series, I used the entire study period as window, and I allowed multiple outcomes as is usual practice with this design. Symmetry analysis, considering only first incident prescription and first outcome in study, and looked at the distribution of sequences. Tested scenarios, 2 different baseline incidence rates, 5 different incidence rate ratios reflecting moderate and strong positive and inverse associations, as well as null association. Degree of misclassification, 0, 2, 5, 10, and 20%, and proportion of chronic users varying between 10 and 90%, and I did that by selective sampling of the users. I had thereby 250 different scenarios, 5 different designs, used 2,500 replications for a total of 3 million analyses with 12,000 individuals in all of them. Analysis followed the usual practice within each of these designs, except for the case crossover and case time control. I used the Mantel-Henschel method instead of usual conditional logistic regression, because I expected a lot of exposure collinearity with chronic use, and there the Mantel-Henschel estimates perform better. Bias was expressed as a log of the estimate of the biased estimate versus estimate of the unbiased estimate, and the confidence interval width expressed as the ratio of the upper and lower limit with the same value of the unbiased analysis as reference. Let's see. If I varied the proportion of misclassified exposure in a baseline scenario of 80% chronic users, incidence rate of 2% per year, and incidence rate ratio of 10, I found quite a lot of bias with the case crossover, case time control, and self-control case series with as little as 2% misclassification, and it rose to outrageous proportions with further proportions, with higher proportions of misclassification. The cohort design and particularly symmetry analysis seem to be much less affected by this. If I varied the proportion of chronic exposure, I would see this problem beginning to be really serious when that proportion exceeded 50% in a baseline scenario of 5% misclassification, an incidence rate of 2% per year, and an incidence rate ratio of 10. If I varied the incidence rate ratio, I saw an upward bias for inverse associations and a downward bias for the positive associations, consistent with this being a matter of non-differential misclassification. I also saw that for inverse associations that were strong, of an equivalent strong to the positive associations, there was numerically less bias for some reason. The baseline incidence rate had no effect on the amount of bias. And I also could confirm the width of the confidence interval decreased with increasing exposure misclassification. At the most extreme, the ratio of the upper to lower limit was half of what it should have been, or rather as it was in the unbiased analysis. The log transform values that are presented to you may not give you the full impression of how toxic this misclassification is. If you look at the case crossover design, there's an unbiased estimate for 0% misclassification, but with only 2 and 5%, it's decreased drastically from the 10 that it should have been, and with higher degrees of misclassification, this association is completely wiped out. You see the same pattern with the case time control design, self-controlled case series, possibly with a somewhat lesser extent. The symmetry analysis seems to be somewhat resistant to this problem. It's not surprising because it only considers the first outcome and the first prescription, so it ignores all of these artificial gaps. I cannot give it a general recommendation, though, because in other scenarios, it would also disregard the true gaps and thereby be biased in situations where the others will not be biased. In addition, it's the least precise of these methods. It has wider confidence intervals for similar scenarios. Conclusion: some self-controlled designs, particularly case crossover, case time control, and self-controlled case series, are hypersensitive to exposure misclassification incurred by too short grace periods, and particularly when there is abundant chronic use, confidence intervals become too narrow. It does not affect symmetry analysis to the same degree, and it's easily understood why. This problem depends on, obviously, the degree of misclassification, and also obviously on the proportion of chronic users, and to my surprisingly on the incidence rate ratio as well. Now you could pose the question, is this really a problem as we use these self-controlled designs? And I believe the answer is yes. In the most recent issue of PDS, Huang et al. Had conducted a systematic review of case crossover studies of pharmacoepidemiology with a focus on recent papers, and they found that only about half of them analyzed single or transient or intermittent exposure. The rest of that, either fully chronic exposure or mixed pattern. And these, I believe, are vulnerable to this problem. So thank you for listening to this, you my IGBE heroes.
Thank you, Jesper, and I think you're also a hero because you're presenting at this early hour. And thank you for the clear presentation. The floor is open for discussion.
Thank you, Olaf. Good morning. I'm Sean Hennessy from the University of Pennsylvania. First, I want to thank Jesper for not only presenting here, but also chairing the session in Argyle too at the same time.
Yeah.
So you're clearly using the clone sensor weight approach this morning.
Yeah.
Grace periods. So in a grace period, there's a period where we think that there might be exposure because of poorer adherence. And if we call that exposed time, it seems like we'd be introducing misclassification, which might be worse in self-controlled designs, because in a cohort study, we would just discard that time. Whereas in a self-controlled design, we're taking time that is actually unexposed and calling it exposed. And yet you're talking about making grace periods too short, and that I'm not understanding why they would be too short. If anything, it seems like you'd be introducing error by making the grace periods too long, and that one way to handle it might be to call those periods indeterminate, so neither exposed nor unexposed, and just throw that time out. So that's one point. And then the second one I just want to throw out there is, even with chronic, so we know that there's an adherence problem. People don't adhere to their medications, chronically administered medications. So if there's non-adherence, then wouldn't that create intermittency in exposure? Thank you.
I think you raise a very important and valid point. I have a backup slide covering some of the recommendations and solutions, and you point to the fact that we really don't know when the patient is taking the medication. Could also be that they're actually more likely to take the medication before the next prescription is filled, because then they run out of supply. We really do not know when that non-use period is. A colleague of mine, Henrik Støvring, has worked with a model of probability of being exposed according to the intervals between the prescription, and that might offer solution when we, as an output of that, do not dichotomize to either being exposed or unexposed. I think some of this problem here arises because of that liability to dichotomize, and if we could use probability in some sensible way, we may get around it. But that's would require a lot of work to demonstrate that would work. But you raise a very valid point.
All right. Thanks, Jesper. For the sake of time, we really have to move to the next presentation, and I want to let you go to your other session, Jesper.
Thank you. Next, we have Mr. Albert Sen-Royal from UMC Utrecht, presenting his study on real-world evidence bridge.
Thank you. 2 seconds. Let me find this out. I get the presentation. I can view here.
This is yours.
Oh, we need to close that one. Cool.
This is yours.
This is mine. Yeah. That doesn't work. Anyway, maybe here.
Yeah, okay.
Keeps not doing it. Anyway, we'll do it like that. I have some notes, so maybe I forget some stuff. But anyway, so my name is Albert. I'm from Spain, and I'm a PhD student at Utrecht, UMC Utrecht. And I'm going to present you the RW bridge, which is a method to connect the protocol with the programming practices. So first of all, I don't have any disclosure what to do. So before I present you anything about the method, I want to introduce the situation where we basically what we do in pharmacoepidemiology. You all know that we go from, we have a population, then we expose it to some drug, some medicine, some pharma, and then we have a research question, what happens afterwards, right? So this research question hypothesis is normally developed, and after the whole procedure, you end up with a statistical analysis plan, which is a very long document, in my experience, written down by epidemiologists, doctors, statisticians, and not normally done by programmers. I'm a programmer. So we go from right to left, very easy. You must know, all of you, how it goes. But then we go from left to right back, and we go from this SAP, the statistical analysis plan, to the analytical program. And this program normally can be written down in R, SQL, Python, name it, whatever. And this process normally then needs to also be delivered to many other databases. So we go from SAP, let's see if this works, SAP, program, we need to deliver to different apps, right? And the DAP is basically a data access provider, like a database, like a research group, or like an organization that provides you data. And then how it works, that you send them the script, you might send it in using different technologies, and they run your script. And then you create evidences. And then you execute your SAP in the code, right? But then we also need this to be really fast. We all need to create evidences really fast. We want to report them really fast, or everything really fast. So it's from a scientific programming point of view, I'm doing my research. This is really difficult. Like it creates just problems all the time. So the idea is to improve all the situation, right? And that's what I'm trying to present here. But we also have, besides, I show you all these 3 characteristics of the whole process, very summarized. We have communication internally. We work in big teams. We have many different profiles of people, epidemiologists, name it, doctors. And then on the right side is me there. And I'm talking all the time with the PI and with the statisticians and with the statisticians and so on. And this normally goes around what is written in the SAP and what needs to be done in the analytical program. And this ends up like this, clearly. Like we see the same number, the same figure, we clearly understand 2 different things many times. Yeah, I guess you can imagine that. You probably have some situations in mind. On the right side is me, obviously that's a 9, and the other side is the PI, it's a 6 for him, but no, he's wrong. And why is this? Well, the SAP is normally written down, it's written down in natural language, hand, and even though it can be very precise, it's not as precise as math. And coding is really similar to that. 1 + 1 is equals to 2. You can write it down, maybe you do some typos, yeah, it's not the same. So this is one of the first controversial points, where written down descriptions of steps you need to do into the analytical program might not be enough detailed to be developed. The second part is, if I remember, because I had in notes, it was basically that this document might change through time. This, like, you have these really long projects, at least the ones I experienced. You might have different deliverables throughout 2 or 3 years. And between deliverables, you might have the SAP changing. And that's also a factor where the whole discussion starts, like you have all a back and forth discussion again about what it is written down, what it has been done, and so on and so forth. Third thing is that the DAP, the data access provider, it also uploads data all the time. It's like constantly updating. They also need to go through ETL process, extract, transform, and load, which is also a factor within the whole formula. And that might affect also how it's the analytical program written down. Because let's say my DAP changed from ICD-10 to ICD-9, which we don't think, but just as an example, metaphorically, like theoretically, then that will affect my code, how I need to extract the data. So basically, this is how it goes. We have a lot of communication, and sometimes this doesn't work. A lot of misunderstanding, which is completely understandable. It's fine. But what I pretend is to create this leverage the connection between both sides by including a new member in between, which is the RW bridge. And this gives balance to the communication. So the idea is to have a metadata model, which has a methodology also how to fill it up and how to expand it, that links the SAP and the analytical program. What we can do with this is, like, we can take the PI's knowledge into the metadata information, metadata model, in a systematic and flexible manner. Because we need to make it flexible, because I mentioned the SAP might change through time, the DAP might change, we need to update the code, so on. So we need something that's flexible, but we also need to have it very clear in order to bring the PI's knowledge inside. At the same time, because we need to make it all this really fast, really fast, we need to standardize the process as much as possible. Because standardization brings optimization. If I always expect the same input, I can optimize my code to that input, right? And so how we do this? So really simple, using relational database design. Here you have an example. This is an example I found in the internet, so you might find it if you Google it. This is a relational database, which basically you have information about different users, their names, their emails, the movies that they have watched and they have rated. And here you can see ratings and some tags that you can use for keeping some other information. So we can understand here that we can see we've been categorizing information from the users on different names, and then we relate them to movies. We can do the similar thing with the SAP. We can take a look what is being described in the SAP in terms of variables, which might be including outcomes, covariates, exposure variables, and we can input them into the same data structure in order to have a visual document. At the same time, we can use it for our program in order to have all the information from the SAP in there. Obviously, it's not all of it. SAPs are more complex than that. Sometimes you cannot fit everything inside. But the nice part of, I hope you can see it, but maybe not. The nice part of programming is that you can be very flexible. So you can include some really hard-coded parts of the script being an option within a metadata file, which is steady and available for DPI. So this is the current status of my research. This is the model right now, and it is basically structured in 4 different regions of the model of what you can translate from here into the SAP or backwards, and it all evolves around the static variables. So the main idea is to start by categorizing the static variables from what they are, exposure and outcome, a covariate, how they are generated, if they are generated combined with other variables, if they're alone, if they need a static population to be defined. So let's say only people that has myocarditis, it really has a very specific population. We also allow here how to create the static cohorts. Obviously, static cohort, I don't know how much time I have because I cannot see it here.
3 minutes.
3 minutes. So, and we can create static cohorts through that because a static cohort normally is defined by an index date, right? So it's index date, when it's been exposed, it's also a variable that we can define. So this is the current status. That's basically it. We're gonna soon preprint it and have it available to all of you if you're interested. You can also contact me if you're interested how this works. And yeah, it's under development. There's no results, obviously, because there's a methodology and a metadata model, so I cannot present you anything in terms of results as other people does. But that's it. Thank you very much. If you have any question whatsoever, just comment.
Thank you very much. We might have a time for one quick question.
This is so quick, so we will probably do another one, just pointing to the special issue on transparency and reproducibility in pharmacoepidemiology and drug safety. I mean, guest editors, I think such work would fit very wonderfully inside such a special issue in the Society's journal, just making you aware of that.
Thank you. That was really fast, but yeah, that makes the whole process really transparent, obviously. So actually yesterday, there was this discussion about code sharing. And there was the whole 1.5 hours about it. And actually this helps a lot because that can show what it is in the SAP in a different manner, like besides graphs, besides plots, and besides sharing the code directly. So you can have like something sustainable and physical that you can see, okay, this person listed these variables, they are being used for this study and they are categorized in this way. So yeah, indeed, I agree completely. Thank you very much.
Thank you very much.
Thank you.
Right. We move to the next presentation by Jonas Walheim from BMS. And his presentation is about diagnosing informative left truncation due to delayed cohort entry in clinical genomic real-world data.
Yeah, thank you for the introduction. And yeah, I'm going to talk about diagnosing informative delayed entry due to left truncation in clinical genomic data. So me and my co-authors are all employees of Bristol Myers Squibb. And yeah, I'll give a brief intro to the topic, and then I'll explain how we can assess dependent delayed entry quantitatively and qualitatively. And then I'll guide you through a little application, how we used it internally for 2 cohorts that we were using in preclinical research. And I'll conclude with a discussion and outlook. So what do we mean by delayed cohort entry? Thing is that in many of our cohorts, we require patients to have some genomic information, some transcriptomics, mutation data, and usually because the biopsies that lead to this information are not standard of care, this often happens only after the index date of an analysis. So I might look at survival after first line of treatment initiation, but sequencing on biopsy and sequencing happens only at a later point. And if I do a survival analysis, by definition, all these patients must have been alive until they had their biopsy. And so if I don't account for this in the survival analysis, it will be overly optimistic. This has been known for a long time, and the standard approach would be to just adjust the denominator in your survivorship estimator. So you just include patients who already met all the inclusion criteria, including biopsy. But this assumes that the delayed entry into a cohort is not informative of the chances of suffering an event. And just a little illustration how that looks in practice. So you would have a cohort with delayed entry, you have this unadjusted survival curve. And then if you adjust for the fact that they only were at risk of dying after they had the biopsy, you have a substantially lower survival curve. And also on the right, you can see the difference between the unadjusted risk set size. So there we assume that all the patients from the beginning would be at risk of suffering an event. But then if you account for the delayed cohort entry, actually the risk set is much smaller. So patients only enter the cohort over time. And it's also interesting to see that whereas normally we start with a large number of patients that decreases over time, if we have delayed cohort entry, it can also happen that we have this low number of patients in the beginning and then it goes up before it goes down again. But yeah, this all assumes that delayed entry is not informative of the event. And this is what led to this research project where we were asking ourselves if this really holds for the data we work with. And the quick answer that we already found in literature is no. There's been a bit of work showing that delayed entry time and event time in that kind of data is often related to, that the biopsy is often related to patient outcomes. So yeah, this assumption of independence is not really met. And there was also some recent simulation study by Ken Kale showing that this informativeness of delayed entry can lead to heavy bias. And so the questions we wanted to answer was whether we can reliably confirm independent delayed entry and how. And then if it doesn't hold, whether we can assess the extent of the bias. And then also we were wondering if we can somewhat correct for the informative delayed entry. So yeah, let me jump right into how it can be assessed. So it's not so assessing dependencies between delayed entry and survival time is not that easy as it seems at first, because you only can observe a part of the underlying distribution. So here on the left, we have simulated data of independent entry and event times, but because in reality, we only see those patients who made it into a cohort. So all those who died before they would have had their biopsy, they are not in there, even though the underlying distribution is independent. If you look on the right, and we would use something like a Pearson correlation, you would obviously see some dependence. And that's something that already has been known for a long time. And like Tsai and colleagues already 30 years ago, they came up with this notion of quasi-independence, where you only compare pairs of patients who had an overlap in time at risk. So intuitively, one can think of this as that you span different rectangular areas in this lower upper left part in your plot, and you only compare you only assess independence in there. And yeah, based on that, you have different metrics. You can have a conditional version of Kendall-Tau that only assesses comparable pairs. You can also have a Cox proportional hazards model, which is only dependent on, which only has delayed entry time as independent variable, and assess dependency between entry time and event time like this. And worth mentioning is that with these approaches, the different samples in the dataset are given different weight because some patients are comparable to a lot of other patients, others are not. So there's not every patient goes into this metric with equal weight. And yeah, because of that, we thought it would also be nice to have some more qualitative visual assessments. So for all of our cohorts, we would usually first look at some scatter plot of truncation times and event times. on the one hand, this helps us to identify clusters of points which would never be compared because there's no overlap in risk. And there were some cohorts which had obvious dependency, but just because there was no overlap in the time at risk, the conditional Kendall Tower showed us no dependency. And then it can also help us in identifying obvious dependencies, because if independence would hold, then the joint distribution of truncation and event times could be described as a product of their marginals. And often just from looking at the data, we can say there's no way that this is true. And then a very intuitive approach, which is nice to share with people who are not as quantitative, and was something that we took from Bakenroth and colleagues. So they said that you can just split your cohort into those patients who have delayed entry and those who don't. And then you do a resampling experiment. You draw from samples from both of these groups, and you produce different ratios of delayed entry versus non-delayed entry. And then you can see how the survival time moves. And if independence would hold, then the survival curve should not move at all. Whereas here we can see it moves, so there would be delayed entry. And then sometimes you do not have many patients without delayed entry, or you would say that those who were biopsied at baseline are already at baseline different than the other patients. And then you can also stratify by patients having a larger or smaller delayed entry time. So we, for example, just that we stratify by having a delayed entry time larger or smaller than the median. And yeah, so this is the set of assessments that we usually apply for cohorts that we have in preclinical research before running any downstream analysis. And yeah, I'll just guide you through 2 examples of cohorts that we assessed. Unfortunately, I'm not allowed to disclose the exact indications, but both were solid cancer tumors. And here we see the naive unadjusted survival times and compared to the survival times adjusted for delayed entry. And we can see that it has a massive impact for both cohorts. Median survival time is about 50% lower. But then the big question is, can we trust these estimates, or are they still biased? And yeah, to this end, we can look at the quantitative metrics. So we can see that for cancer X, there's not much or no evidence of dependency. For cancer Y, we have quite strong evidence of dependency. Patients who enter later, they live longer. And yeah, doing a quick visual inspection of the distribution of truncation and event times, you can see that there's no clear red flags. There's also no problem with samples not being compared too much. And so then we also checked this resampling experiment, and we can see, similar to the previous slides, that there's no influence of late cohort entry for the cancer X, and for the other one there is dependence. So yeah, to summarize that analysis, we can see that delayed entry has a really strong influence on overall survival for both of the cohorts. And yeah, looking at these independence metrics, we can see whether we can trust this risk set adjusted estimate or whether we should still be careful. And for cancer X, we can see that there's minimal evidence of dependence, so we can just go ahead with the analysis of the cohort. Whereas with cancer Y, we could see that there is still quite some bias. So for all the downstream analysis, we need to think about additional sensitivity checks to make sure that we are not having any bias and not having too much biases there. And yeah, so to conclude, we could see that adjusting for risks, doing risk set adjustment to account for delayed entry should always be done if we have delayed entry in a cohort. And then, but this is not enough. We also need to check if there's still some bias in the risk set adjusted estimate, because the biopsy might be informative of patient outcomes. And yeah, as a bit of an outlook, a big problem that we have in this project, in this topic, is that we cannot formally prove the absence of dependence. And what we are currently working on is to set up tests that we could at least prove the hypothesis that the degree of dependency is not too high. So maybe we could say, okay, the per year of delayed entry, the hazard ratio doesn't change by more than 2% or by 3%. It all depends on the precise project and how much of an effect size we expect. Then something else that would be really nice with larger cohorts is an inverse probability weighting approach by Vakulenko and colleagues, where you would just model the dependency and then account for it. But you need to have much bigger cohort sizes than we do. And you also need to know which variables are responsible for delayed entry, and you need to have them properly documented. So this is something for other cohorts that we might get our hands on in the future. And then also worth mentioning is that for other endpoints like PFI, the risk set adjustment approach is not applicable. And at first sight, you might think that delayed entry does not matter, but if there is a strong link between this endpoint and survival, you might still have some delayed entry bias, because maybe patients, after having a disease progression, they would die a couple of months later, and then they are also not included in cohort. And yeah, another thing that was recently published is that you also need to be careful with intra-cohort heterogeneity. If you have different groups of patients with different relationships between the delayed entry and event times, sometimes your overall estimate at a cohort level would say delayed entry is independent, but actually it is not. So yeah, this was everything. And yeah, as you could see, there's still quite some things to be done, but I hope that was a bit of an insight in what we are doing in this field. And if anyone wants to discuss, collaborate, please reach out, and happy to hear from you.
Well, I think that was a lot to absorb, I think. Any questions from the audience? Please step to the mic if you have a question. Okay, not seeing anyone yet. So I was wondering, there may be different reasons for taking a biopsy, but also for in other situations when you take samples from patients, it may be for let's say selecting a cohort. It may be for maybe identifying effect modifiers or as a risk factor. Does that matter for this problem, you think? Because I can imagine if you maybe retrospectively assess some biomarker or a genetic variant which is stable over time, it doesn't matter when you measure it, that it would not be such an issue. But maybe I'm wrong.
Yeah, great point. Absolutely, it matters a lot whether you, like, what reason the biopsy is being taken for. We also had quite some discussions with collaborators who said they never would expect a increased survival chance with a later biopsy, but sometimes there's quite some evidence that often biopsies are prompted by disease worsening, and then if there would be this negative relationship that patients with a late biopsy will not live as long as patients who have it earlier. But then you might also think of cases where maybe a biopsy is being taken for targeted therapy, and then the patient gets targeted therapy and might live longer than comparable patients who do not get a biopsy. So yeah, it depends a lot. And that's also this point with the intra-cohort heterogeneity, that sometimes biopsies are taken for one reason, sometimes for another, and the relationship will be different. And if you don't account for the different reasons, then the overall estimate might still not be the right one.
Yeah. But still good to explore that because you never know in advance whether it has an impact, I think.
Yeah,
so
absolutely. Yeah.
It's a good point. All right. Any other questions from the audience? No. So still one last question, maybe. So does it help to take a different approach? So this is for like cohort studies, but if you'd say, okay, we are interested if you would apply a case control study, for instance, within that cohort, would that still be an issue, you think?
Well, that's a good point. We didn't think about that so far. Yeah, let me think.
Because you do not really take, let's say, it's not a time to event analysis, so it's sampling from the cohort, and I can imagine that then, because the biopsy has already taken place, you cannot answer all the questions, of course, that you would like with the case control study, but for relative measures of association, it might also be a way around it.
Well, we didn't really look into this because for the kind of research questions that we have, case control is not an option.
Sure. Okay.
Yeah, that would be something interesting to look into.
Okay. Well, thank you.
Yep.
Okay. Next we have Ms. Catherine Vino from UNC Chapel Hill, US, presenting on an analytic method to weight longitudinal treatment patterns for visualization with Sankey diagrams.
Good morning. My name is Katie Weiner. This certainly falls under other methods stuff for this session, I would say, but hopefully come along with me on this ride and we'll see how it goes. I'm here to present an analytic method to weight longitudinal treatment patterns for visualization with Sankey diagrams. For disclosures, I am a current epidemiology PhD student at the University of North Carolina at Chapel Hill. This work was additionally supported by Target RWE and inspired by several projects that I have worked on in collaboration with them. Just a quick overview, just to make sure we're on the same page. I was going to do an introduction to Sankey diagrams so people can understand what they are. And I will then go over a method to address informative right censoring for visualization, talk about a really quick kind of illustrative simulation and the results, and then conclude. So a Sankey diagram is a descriptive tool to visualize treatment patterns like treatment initiation, switching, and discontinuation. It's essentially a bar chart connected by flows. Vertical bars represent the proportion of the population in that treatment at that time point, and the horizontal flows they represent the proportion flowing from one treatment to another. The uses they can officially depict data otherwise difficult to present in a tabular format. So they can help us understand treatment utilization, treatment progression, and understanding clinical treatment guideline adherence. If you're trying to understand optimal treatment regimes, it can help choose a dynamic treatment regime to study. And it can be useful in visualizing patterns other than treatment. For example, understanding disenrollment patterns from health plans. A quick overview, we define a pathway as a set of treatments that the patients follow we define a pathway as a set of treatments that the patient follows. So each of these arrows on the diagram is one pathway that a patient can take. This is a fairly simplistic example where we just have treated and untreated states, and a patient has to initiate treatment to be included in the diagram. So there's really only the 4 pathways. You can imagine that this can get out of hand very quickly for visualization. For example, if there were 5 treatments and 5 time points, the resulting pathways would be 5 to the 5th power, which would be over 3,000 pathways to attempt to visualize. For our purposes and for estimating these pathways, we conceptualize the pathways as arising from a multinomial distribution in the population. In this particular example, each of those 4 pathways just has a 25% prevalence in the population. Unfortunately, longitudinal data is often subject to right censoring. We're all familiar with dealing with this, but think about disenrollment in claims data or loss of follow-up in prospective cohorts. Informative censoring can bias even descriptive statistics. And if censoring is informative, presenting only the treatments for subjects for whom we have full follow-up in our cohort can lead to selection bias and a misleading representation of treatments in the population we are trying to describe. So our objective was to develop a method for visualizing treatment patterns with Sankey diagrams and data subject to right censoring. To do this, we've applied inverse probability of censoring weights methodology to estimating treatment transitions. With this method, we aim to utilize as much follow-up information as possible from each cohort member in order to minimize potential selection bias. So recall each treatment pathway is the treatment flow through the time points. We want to estimate the probability of each pathway. At each time point, we depict the treatment as A sub the time point, and a treatment pathway, so a treatment history would be A bar sub K, where K is the total number of pathways. The table enumerates the 4 pathways that were shown on the previous slide. Again, fairly simplistic. And we're also just kind of showing this, that this is just the intersection of the treatments. It's a deterministic pathway in the population. And so what we want to do for a Sankey diagram is just find the probability of each pathway. That is our target. So we're going to have an estimate for each possible pathway. So we can rewrite the joint probability as the product of conditional probabilities. And again, the uppercase K is the total number of time points. Lowercase k is the time point that we are like that particular time point. Going back to the high dimensionality that can affect this estimation, if we're trying to estimate the probability of a time point based on a treatment history, it can get fairly out of hand, especially if we have rare treatment pathways or patients who have, we're like having a lot of patterns of discontinuation and initiation. We can run out of patients in that pathway. And that's where we kind of can run into a quasi-positivity problem. We don't have someone to stand in for that pattern if they're being censored. So to get around this, we applied a Markov assumption that treatment transition probabilities are actually independent of treatment history. And this is a very strong assumption. And again, this is a way to present patterns for visualization. This is still descriptive statistics. And really, you only need to apply this assumption in that high dimensional space where you're going to be running out of history when people are censored. Like just for an example, if all patients with a particular history are censored at k-2, the probability of each treatment at k-1 will be 0, and then those pathways don't end up in the diagram. So that is why we have this Markov assumption, so we can independently assess these transitions and multiply them together to get back to the joint probability. And then we get to the informative censoring part. So for this, we want to estimate the probability of being uncensored at each time point. To account for informative censoring, we can weight each treatment transition by the inverse probability of being uncensored at that time point. We define this here as the conditional probability of being uncensored before each time point, conditional on a censoring model, which mostly just needs the fact that you haven't been censored up to that point. And this is where you can incorporate treatment history in a way to account for a person's history for being censored or not. And then optionally this says baseline covariates, but I think time varying covariates are fine too. And then we weight them by just the inverse of that probability. For our purposes, we use logistic regression at each time point. And then we can weight those individual treatment transitions by that inverse probability and multiply it all together. And then we get our estimate for the treatment pathway. That estimate, the p hat a bar sub big K, is just the estimate for one pathway. So we do that for every single possible pathway. And then we have the full set of treatment pathway probability parameters from the population. I'll very quickly go over the simulation, which is an illustrative example. First, we generate the sample with treatment pathways following a multinomial distribution. For purposes of the slides, we just have the 4 pathways with a sample size of 12,000. We have 2 scenarios. We induce right censoring on the cohort. In scenario 1, it's non-informative censoring. In scenario 2, it's informative censoring based on prior treatment. And then we estimate the treatment pathway probabilities in 2 ways. First, naively, without accounting for censoring, and I call that a complete case Sankey. And all that is taking patients who have individuals who have full follow-up in the population and just using them to create the Sankey. And then we apply the inverse probability of censoring weights methodology and compare the 2 types together. For scenario 1, non-informative right censoring, the bias is extremely small and very comparable. Flows with less patients are a little less biased in the weighted, where larger flows are less biased for the complete case. What's interesting, very minutely, and again, this is descriptive, but the variance is a little bit smaller in the weighted, and that's because we can use more information from the patients when we're censoring them. So the complete case, we can be slashing our sample size. So slashing is kind of a strong word, but we can we have more information when we're using the weighted kind. In the second scenario, informative right censoring, we see a much smaller bias in the weighted Sankey and also smaller variance. And again, we can use more information from the weighted, and we have more observation points coming into the estimation. This is the same 4 treatment pathways with the informative right censoring. On the left, we have the true treatment pathway parameters in the population. In the middle, the complete case, and on the right, the weighted. This is the 4 pathways that each truly have 25% parameter in the population. And we can see we are overestimating the patients in the complete case who are being treated in this particular scenario. And that continues, but a product of the way that the distributions had the 25% chance of switching at each time point. We have some gains at the end. But yeah, you can see the weighted Sankey more closely follows the truth in, or how we define the truth in the population. Finally, Sankey diagrams are a useful tool to help us understand treatment initiation, switching, and discontinuation in a population. However, right censoring complicates creating these visualizations, and these different approaches may depend on your question of interest. We obviously did not talk about every way to make a Sankey. And here we have proposed a method to incorporate inverse probability of censoring weights to estimate treatment pathways. Limitations are the high dimensionality issue that I mentioned. It does require correct specification of the censoring model. And the way that we define these Sankeys for our purposes, we're cross-sectional. They were cross-sectional evaluations of being on treatment at these pre-specified time points. So it doesn't necessarily capture treatments between time points, although you could probably alter your censoring model to address that. Thank you.
Thank you very much for the presentation. We can take a few questions.
Very nice and interesting presentation, Henrik Storbring from Denmark. You mentioned this strong Markov assumption you have, and the typical trick of getting around strong Markov assumptions in multi-state models is always to introduce some sort of covariates. So even though you do not capture the full treatment history until then, you might think about introducing covariates that could capture important parts, and that might sort of get around that assumption. Have you been working on that?
I have not, but that's a very good idea. Thank you.
So sorry, this might be very basic, but so one of the purposes that we use Sankey plots could be that we want to see how many of the patients do get censored or do change state for different reasons. Could you sort of remind me how the interpretation is different for the IPC weighted ones and sort of the usual Sankey plots?
Yeah, that's a very good point. And actually, one of these Sankeys I kind of briefly mentioned about visualizing health plan disenrollment does exactly that, right? Like, we're interested in how people are leaving the population. And I think how you want to display the patterns just depends on your question. So if you're interested in what censoring looks like in your population, or who's being censored the most, then yeah, this method, you wouldn't use this kind of methodology. But if the question of interest is, what do patterns look like in the population? Like, if that is specifically your population, I want to know what how patients are transitioning from one treatment to another, how they're adhering to treatment. I think that this applies more so, because the censoring could possibly take away from that, or could present, even if we had a censored state in the Sankey, because it is a proportional plot, it could still give us misleading proportions if we're kind of taking the censored patients out of the denominator or leaving them in the denominator. You know, I think then you kind of get into this question of what to do with those patients if really you're just interested in the proportion in each pattern.
So we would be looking at sort of a change in state when if there were no censoring for these patients who gets censored.
Sorry, could you repeat that?
Would we be looking at a sort of the change in state over time if there were no censoring events?
Yeah,
in the
exactly,
population?
exactly.
Great. Oh, sorry.
Hi, good morning.
Morning.
Sarah Vidito, Aetion. I'm curious if you've compared your IPC weighted Sankey's to the variable follow-up Sankey's where you allow for sensory. I think you touched on it just a little bit, but I'm curious to hear your thoughts on benefits versus anything else you might want to consider if you're thinking about this versus just censoring patients for their variable follow-up during the Sankey.
So you mean like presenting them in a censored state or level?
Exactly. So at each of the nodes, instead of having your denominator be the overall number of patients, it would be the number of patients still remaining at that point in time.
Yeah, and I think if you don't have informative right censoring, that makes total sense, right? But I think if censoring is informative, then even using the patients left at each time point can give potentially biased proportions at each time point. And so, I mean, it depends on your question and what exactly you want to know. So that's, I think, where the methodology comes in. And the complete case is not exactly that, but in the case where the patient's being censored or the patient staying in the population is just a random sample, then I think that is definitely the way to go. It's easier.
Thank you.
Thanks.
Thank you very much.
Thank you. So the next presenter is Adam Streeter from the University of Münster, Germany. And he's going to present on adjusting von unmeasured confounding in the statin treatment options during vaccination against flu study.
Okay, so yes, hi, I'm Adam Streeter, and I'm just going to talk about some methods that we use to adjust for confounding bias from both observed and unmeasured sources in the STOP flu study, which is a study of looking at the potential modifying effect of statins on flu vaccine effectiveness. So this was funded by the UK NIH, and I've got no further conflicts of interest to disclose. So if we think about how we might go about investigating a potential interaction between statins and flu vaccine, we could select patients within one level of one of the exposures and then compare the levels across the other exposure. And that's indeed how it's been done in other studies investigating this question, and I'll show you a bit more about that in a minute. So we could select patients who received the flu vaccine and then compare those patients who had received statins around the time of flu vaccination to patients who didn't receive statins, and that might tell us something about the potential modifying effect of statins on the flu vaccine. However, to rule in or rule out a direct effect of statins, then we might like to compare those results to perhaps another cohort of unvaccinated patients looking at the same effect of statins. And similarly, we could do something else. We could look at the flu vaccine effectiveness in a cohort of statin prevalent users and compare that to flu vaccine effectiveness in patients who weren't on statins. So the STOP flu study looked at all four of these cohorts, but for today's presentation, I'll just be looking at cohort number 1 there. And I mentioned the other studies. So they used a variety of these cohorts, and I've highlighted with a red one there, those results which pertain to cohort 1. But overall, you can see there's a fair degree of heterogeneity with significant results on either side of the null ratio of 1. So StopFlu used routinely collected electronic health records from the UK Clinical Practice Research Data Link, which is a database of pseudonymized data from patients in primary care at practices registered to the CPRD, and it's got linkage to hospital mortality and socio-economic data. So in the absence of routine testing for flu, of course, we had to rely on a proxy outcome, and this was flu-like acute respiratory infection. And we identified those outcomes in the data using codes published by the London School of Hygiene and Tropical Medicine. And these were composed of diagnoses both in primary care and in hospital, and were endpoints in a survival analysis of survival time since the date of vaccination. Secondary outcomes we also looked at were general ARIs and pneumonia-like ARIs. And in fact, because the ARI flu was sparsely coded in the data, we found it to be sparsely coded in the years that we were looking at. For today's presentation, I'll be focusing on general ARIs because it better illustrates the differences between the methods. So to adjust for confounding bias, we use a within patient control period. So in that respect, it's sort of similar to self-controlled methods, but we estimated the effect with comparison to concurrent controls, which were fairly easy to define, but also I think offered better control over some of the period varying factors such as annual changes in viral potency and occasional mismatches between the vaccine serotype and the flu virus. So the method we used was the prior event rate ratio method, which uses an exposure-free period prior to the period being studied as a measure of the confounding bias between the two groups. And then we use that to adjust our estimate from the study period. And as you can see, this can be applied to both, well, it can be applied to survival data, but also rate data as well. And there's an alternative formulation called the pairwise method, and that effectively makes the adjustment within each arm first before estimating the treatment effect. And also, interestingly, the pairwise method has its own likelihood. And here, it just draws on information from patients who have had, only patients who have had an outcome in either the prior and or the study period. And both these methods, of course, rely on assumptions. Chief amongst those is the assumption of time invariant confounding. So in StopFlu, we were interested in the UK population of older adults aged 65 years and over. We looked at the years from 2010 to 2018, and because of the requirements of the PER period, the PER method, they had to have had at least 2 consecutive vaccinations over 2 consecutive years. And we were comparing new statin users who were defined as patients who had initiated statins between the 1st of May and the index date of the 1st of September. And they had to have had enough statins to last the 22, at least 22 days of the plus or minus 2-week period around the date of vaccination. These were compared to, of course, patients who had no history of taking statins. They were followed up to the 31st of August. And of course, we applied the PER and the pairwise methods, but then compared those results to a more conventional method, inverse probability treatment weighting, which adjusts for observed confounders through estimating propensity scores. So the results we found were quite remarkable. So the hazard ratios of the results from the naive analysis of the study period are in dark gray, and they're all, as you can see, above the null effect of 1, indicating an elevated risk of general ARI associated with taking statins at the time of flu vaccination. Now, adjusting for the observed confounders, we get the results in blue there, light blue, and you can see they've attenuated slightly, but not much. But when we look back at the prior periods, which are in light gray, we can see they're also all above 1, which indicates that the exposure group had a pre-existing higher risk of ARIs. So we can imagine if we adjusted for that, we might expect to see a result closer to the null. And indeed, once we applied the per and the pairwise method, which are in pink and purple, we got hazard ratios that fluctuated around the null effect of 1. And in fact, aggregating the data over all those years and then analyzing using the pairwise method, we got a hazard ratio of exactly 1 to 2 decimal places. So apart from the conclusion that we found no evidence of a modifying effect of statins on flu vaccine effectiveness against the outcome of general ARI, I think this illustrates the value of quasi-experimental methods such as the per and pairwise methods, which I think can be used at least as a sensitivity analysis to conventional methods that are just for observed confounders. And I acknowledge that the years that we looked at, most of these years, there was a low incidence of flu. So it may be interesting to go and compare these results to other years where there was a higher incidence of flu and see how they might vary using the per and pairwise method. So I think further work could also be done to see how the assumptions could be relaxed, particularly the assumption of time invariant confounding. And I think it would also be interesting to see how this research question could be addressed using purely self-control methods without concurrent controls, and then to compare the performance of those against the per and the pairwise methods. So thank you for your attention.
Thank you. Any questions from the audience?
Yeah, Hector Isurieta, FDA.
Hi.
Nice to see you, Adam.
Nice to see you.
Beautiful study. I was thinking, going back to, trying to find other approaches, something you mentioned, which is that the incidence of influenza was higher in some of your years and lower in others. If I believe 2010-11 is one of those examples, after the pandemic, incidence of flu is very, very low. So I was thinking adding one layer to your study of using a negative outcome, and the negative outcome could be acute respiratory infection during 2010-11, and then use the pair on those years and see what happens there, because it should be a perfectly negative study because of the low incidence.
Yes, I guess that's an interesting way of approaching it, because we used that. Obviously, I can't show all the results because it's quite a big study, but we use a negative control outcome of fractures and also non-thoracic fractures. The problem is sometimes you choose a negative control outcome and you're fairly convinced that it's not related to it obeys the assumptions, but unfortunately sometimes it's also infrequently coded, so you get a result that confirms the result from your analysis, but the confidence intervals can be quite wide. So I think that the hunt is on always for a suitable negative control outcome.
Right. I just one small question. One of the key assumptions of the prior event rate ratio control method is also that the that prior events are not related to subsequent exposures. You didn't mention it, but have you considered that at all?
Yes, we do consider that. Yes, you know, it's never quite perfect, but it's as long as it's not too strongly indicative of subsequent exposure, then simulation work has shown that it's doesn't bias the results by too much. You know, and of course we're applying both the per and the pairwise, which are sensitive to different degrees to these assumptions. So some, you know, one method can be more robust than the other.
And then it's consistency also.
It's consistency as well. Yes.
Okay. Great. Thank you.
Thank you very much.
For our last presentation, we have Dr. Christian Lund from University of Southern Denmark. He will be presenting his study on the relationship between sequence ratio and incident rate ratio.
Yes, thank you. Wonderful seeing such a huge crowd here, especially that you stick through all of these presentations, which were wonderful. As said, my name is Christian Lund, and I'm a postdoctoral researcher at the University of Southern Denmark. And what was also invented at the University of Southern Denmark is the sequence symmetry analysis. Therefore, I'm giving this talk today entitled "Is the sequence ratio an unbiased estimate of the incidence rate ratio?" which I guess is a good question. These are my conflicts. I don't think they apply to anything today. But just to ensure that we're all on the same page, I'd like to briefly recap the sequence symmetry analysis. So consider two things: a drug exposure, drug initiation, and an event of interest. So we have the drug, we have the event. If there's no relationship between the drug and this maybe even adverse event, then we would expect this sequence of drug to event to be equally as likely as the event to drug sequence. But if the drug causes the event, we would expect the above sequence to be overrepresented. Okay, from this we can calculate a sequence ratio, which is the easiest effect estimate, as it's just the number of drug to event sequences divided by the number of event to drug sequences. Easy. So just to show you why this is important, I did a PubMed search on the sequence symmetry analysis. As you can see, it was invented here in 1996. Uptake was slow, but during the last 10 to 15 years, there's been substantial uptake. And I fitted a proper model to show you that this is a very important research question to understand the foundations of this exponentially increasing popular method, okay? So, it has been applied to beneficial effects of drugs, it has been applied to quantifying prescribing cascades, and it has even been applied to drug safety signal detection, where all kinds of drugs were tested for adverse events. Let's rewind a bit and go to the original article back from 1996. It was Jesper Hallas, who we've heard previously today. And he writes, let me just read this out. On a theoretical basis, the ratio of RC divided by RN, which is the sequence ratio, can be shown to be identical to the incidence rate ratio that would have arisen from a cohort study. On a theoretical basis. You may not be familiar with this paper, but there are no proofs. There are no simulations. There's nothing. We're just taking his word since 1996. This is shocking. So that's why me and my colleagues, we actually wanted to investigate whether the estimated sequence ratio is an unbiased estimate of the incidence rate ratio that arises from a cohort study. Good. Now, I'll present to you the data generating mechanism, or in more plain language, just the scenarios that we analyzed. Okay, first of all, we simulated populations of 100,000 individuals who were followed for 5 years. They could not die. They were all there for all 5 years. And they could initiate a drug of interest. The rate of drug initiation was 1 initiator per 50 person years, and they could only initiate the drug once. Event times were drawn from an exponential distribution. Then also we simulated an adverse event of interest with a rate of 1 event per 10,000 person years and up to 1 event per 10 person years and some in between. Finally, the event rate could be modified by an incidence rate ratio after drug initiation. We tested incidence rate ratios of 0.2, 0.5, 1, 2, and 5. That's it. This is a very simple simulation. We also tested slightly more complicated scenarios, one where the event of interest was deadly, where a given proportion of individuals could die of the event of interest. And we also tested another scenario where the event of interest reduced the probability of being exposed in the future. Right, the estimators that we tested were, of course, one, a cohort study. We just counted all unexposed and exposed person time, calculated incidence rates, and calculated the basic incidence rate ratio. We also, of course, used a sequence symmetry analysis. We used the exposure index variant, where we had observation windows 365 days before drug initiation and 365 days after drug initiation. So how did we evaluate the performance? Well, of course, our main measure of interest here was bias. Bias was defined as a logarithm of the estimated sequence ratio minus the logarithm of the true incidence rate ratio. Finally, precision was also of interest. We calculated the empirical standard error, defined as the square root of the variance of the estimated sequence ratios. And now, without further ado, the results. Okay. Please bear with me, this may not be entirely conventional to present it like this, but what we have here are all the simulated scenarios and all iterations of our simulations. So what you see is actually on the x-axis, we have the 2,500 iterations for each simulation and the point estimates. On the y-axis, we have the estimated incidence rate ratio for each plot. The columns represent the different outcome rates. So we have on the leftmost side, very rare outcomes, and on the rightmost side, frequent outcomes. Then the rows represent the simulated incidence rate ratios. So in an unbiased method, we will see that if we have a true incidence rate ratio of 0.2, as you can see on top, we also want all the dots to lie around 0.2, right? Which they kind of do. 0.5, we want it around 0.5. 1, 1, and so on. So as you can see, a cohort estimator estimates the true incidence rate ratio. Now to the symmetry analysis. Looks pretty good, I would say, right? We can do the same thing. True, 0.2, sequence ratio 0.2, 0.5, 0.5, 1, and so on. Well, I guess this looks okay, but the first thing that pops up is here, it looks a bit more noisy, a bit more shaky, right? But this is expected. But to really compare, I guess we need both at the same time. All right, so in a perfect world, the red dots from the sequence ratio would align with the dots from the incidence rate ratio. But the first thing that pops up here is, of course, the red dots are more noisy. There's less precision here. But another thing, if you look very closely at the frequent events, especially with the increased incidence rate ratios, is that the red dots systematically align below the black dots. This indicates a conservative bias. This is bad. It's nice to look at this graphically, but let's quantitatively take it in the table view. So the leftmost column is the true incidence rate ratio. Then we have the bias for the estimated incidence rate ratio. We have the bias for the sequence ratio. We have the mean estimated incidence rate ratio and the mean estimated sequence ratio. Of course, we would like the bias to be 0, which it pretty much is for most of the estimated incidence rate ratios. The bias for the sequence ratios, I guess, is okay. Okay. But let's look again at the scenarios we were looking at before. The frequent events. We can see here that there's substantial bias when the events are frequent and the incidence rate ratio is high for the symmetry analysis. So if we have a true incidence rate ratio of 5, we actually only get a sequence ratio of 3.7. If we have a true incidence rate ratio of 2, we only get a sequence ratio of 1.7. Then we have another problem here with very rare events. I'm not too worried because in these simulations, we actually only had about between 1.4 and 3.5 sequences, I mean. So if you did a real study, you would not continue your analytical work. So let's forget about these. Okay, the precision, well, we had empirical standard errors for the incidence rate ratio of 0.15 for the cohort study and 0.2 for the sequence ratio. Not too shocking, the precision is lower. So Last but not least, our special scenarios. Here, we only simulated a true incidence rate ratio of 1.0. The black dots are again the cohort estimates. And this time, if the event of interest occurred, individuals could die with a given probability, which we varied between 0.01, 0.05, and up to 0.9. Okay, so not very deadly events, very, very deadly events. So let's add back the red dots. As you can see here, actually that for probabilities of death of 0.1 and below, there's actually not much bias. Probabilities of death of 0.5 and above had substantial bias. But I would argue in pharmacoepidemiology, it's rare that we evaluate events that are very deadly. So actually, I think this is nice to see. Last but not least, we have the scenario where the event of interest reduces the rate of drug exposure. Again, we have here the incidence rate ratio that modifies the rate of drug initiation. So it's 10 times less likely to initiate the drug after the event. And then we have different values. And as you can see, again, bias increases, the less likely it is that you initiate the drug after the event of interest. And this is actually bad, because no matter what rate ratio modifier we tested here, it actually had a substantial bias. So not good. So in conclusion, back to the original research question, the sequence ratio is an unbiased estimate of the incidence rate ratio in most cases. So except if the event rate is very high, it's not. If the event is very rare, it's not. And if the event reduces the rate of future exposure, it's really biased. Thank you for listening. Thanks to my co-authors, the ICTY organizers, and of course, we also need to thank Jesper Hallas for inventing the method, I guess. Thank you.
Thank you so much for the presentation. We can take a few questions.
I guess it was convincing.
Did you have any other scenarios that you thought about or tried to do?
Yes. We also thought, of course, about trends in exposure, and we worked on that, but actually we decided against it because there's a lot of literature on that already, and we know it's horrible if there's an exposure trend. And then we would also need to evaluate different methods to handle those trends, which again, I think is a different research question. So in essence, we really wanted to keep this short, sweet, and crisp, just to answer this key assumption in all symmetry analysis, that it's actually an estimate of the incidence rate ratio.
Ishihara from Keio University at Tokyo. Thank you for your very entertaining presentation. So just I would like to ask one question regarding what is estimated by the question. So by using the design of crossover design, you are going to answer the question like when is the timing of the exposure. But if we use the design of such a cohort study, who got the problem, something like that. So these designs answers different questions. I mean, so what do in this context, in considering this kind of differences, how do you interpret your results?
Yes. The honest answer is, yeah, well, I totally agree with what you're saying. And this is a question of what is actually the estimate of the sequence symmetry analysis.
Yes, that's it.
I think this is a really interesting question. This has been recently done for the case crossover design by some authors, including Miguel Annan, I think. My answer is I have no idea what the estimate of this sequence symmetry analysis is. I would love to explore this. So if any very capable statisticians are interested in collaborating on defining a proper causal estimate for the sequence symmetry analysis, I would be very interested. I don't think I can do this alone. But after we did that, then I could answer your question, which I think is a brilliant question.
I would like to hear your answer. Me either. I cannot answer this question because that's why I asked.
Yeah.
Thank you so much.
Thank you.
So thank you very much. So that concludes our session. Thank you very much for all the presenters and everyone in the audience to attend this early morning session. Thank you.